Question 1. In an aqueous solution, the acid HCl acts as a strong acid and HF acts as a weak acid. Which of the following are correct dissociation reactions of the acids? So first we need to know that strong acid, they dissociate completely, so we use one arrow. Whereas weak acid, they dissociate partially, so we need to use reversible arrows. So the first option where we have the HCl and we're using a single arrow, it's a strong acid, so this is going to be correct. HF, which is a weak acid, and we're using reversible arrows, this is going to be also correct, as HF is the weak acid. Now for HCl and HF, where over here we use the reversible arrows for a strong acid, this is going to be incorrect. And when you use a single arrow for a weak acid, this is going to be incorrect. What are the correct acid-base pairs? So we need to know that a conjugate acid-base pair differs by one proton, which is H+. So if we look at HF and F-, and if we remove an H+ from HF, we're going to get the F-. So this is a correct acid-base pair. For the H3O+ and the H2O, if we remove an H+ from H3O+, we're going to get H2O. So this is correct. For H3O+, if we remove an H+, we're going to get H2O, and we're not going to get the OH-. So this is incorrect. So the only correct options are these. 25 milliliters of a solution of 0.025 m of HCl is introduced into a beaker. Calculate the volume in centimeter cube of HCl needed to prepare the solution at conditions where the Vm, the molar volume, is 24 decimeter cube per mole, and give your answer to two significant figures. So this is the volume, which is 0.025 liters. I change it to liter. This is the concentration, which is 0.025. So first I found the number of moles, C times V. After I got the number of moles, I found the volume using this equation, N equal V over Vm. We have the molar volume, and we got the number of moles, which is 6.25 times 10 to the power minus 4. So I multiply them, and I get a volume of 0.015 liters. Then I multiply it by 10 to the power of 3 to change it to milliliter or centimeter cube. It's the same. So it's going to be 15 milliliter or 15 centimeter cube. Now question 2, an indicator is represented as HIN dissociates in water according to the following equation. This is the equation that's given. HCl is added to the solution. Which of the following is true? Now HCl dissociates into H+ and Cl-. So HCl will give the H+. So we need to think that H+ will be added to this system. And if H+ is added, we need to remember the Le Chatelier's principle, that the system will counteract this change and wants to decrease the H+ ions. So it's going to shift towards the left side. So, and the solution is going to become red. So the correct option is this one, as the solution turns red, and the equilibrium is going to shift to the left. The range of color change is 4.4 to 6.3. What type of titration is it? So the color change occurred at an equivalence point that is less than 7. This is where the range of color change occurred. It occurred at a pH that is less than 7. Now for strong acid, strong base titration, the color change usually takes place at a pH equal to 7, the equivalence point. So this is wrong. For a weak acid, strong base titration, the color change usually occurs at a pH that is greater than 7 for the equivalence point. So this is also wrong. For the strong acid and weak base, the equivalence point occurs at a pH that's less than 7, which is this case over here. So this is correct. For a weak acid, weak base titration, we need to use a pH meter, as there are no suitable indicators for this type of titration, and it's difficult to find an indicator that's suitable for this kind of titration. So the only correct option is the strong acid, weak base titration. Few drops of the indicator are added to a solution of pH equal 9. So pH equal 9, this is basic, as the pH is greater than 7. What will the color of the solution in the beaker be? So since it's a basic solution, so we need to think that we will have this, the In- present, which has this yellow color. As we know that in a basic solution, the H plus will decrease, and we're going to go this way. So we have this yellow color. So the color of the solution in the beaker will be yellow. If we add excess acid, so if we add H plus, the equilibrium will shift to the left. And if the equilibrium shifts to the left, then the color is going to become red. As H plus increases, system wants to decrease the H plus by shifting towards this side. So in this case, it's going to be red as the equilibrium shifts to the left. Question 3. In an aqueous solution, the acid H2SO4, strong acid, we need to know that the sulfuric acid is a strong acid, when the first hydronium ion dissociates and the resulting anion acts as a weak acid. Now, when H2SO4 dissociates, it's going to give HSO4 minus plus the H plus. So this is the resulting anion, and this resulting anion is going to act as a weak acid. Therefore, in the first step, H2SO4 is a strong acid. The HSO4 minus, the resulting anion, is a weak acid. So we need to use double arrows for this one and a single arrow for this one. So the correct option will be this, as they're using H2SO4 and then they're using a single arrow, showing that it's a strong acid. And it is this one for HSO4 minus, as they're using the double arrows, the reversible arrows, indicating that it's a weak acid. Which of the following are the correct acid-base pairs? Select the ones that apply. If we remove an H plus from H3O plus, we're going to get H2O. This is correct. If we remove H plus, we're going to get HSO4 minus, not SO4 2 minus. This is incorrect. This is correct. If we remove H plus from HSO4 minus, we will get SO4 2 minus. If we remove H plus from H2SO4, we're going to get the HSO4 minus. So these are the correct options. A sample of 25 centimeter cube of a solution of 0.01 m of H2SO4 is introduced into a beaker. Will the pH value be equal, less than, or greater than 2? So the concentration is given as 0.01 m for the H2SO4. Now H2SO4 releases 2 acidic protons, H plus. So if it's 0.01, I have to multiply by 2. The concentration will be 0.02 m. And then I will use the formula, which is pH equal minus log H plus. It's going to be 1.7. Therefore, the pH is going to be less than 2. Question 4. Calcium carbonate CaCO3 react with weak and strong acids where it gives us gas, salt, and water. 2 experiments are done, one using a monoprotic strong acid and another using a monoprotic weak acid, according to the following procedure. So we are given the procedure. We have 10 grams of CaCO3 in excess, and we have 100 centimeter cube of 0.1 m of the acid. And the volume of the gas released after time t is recorded for each acid. Now, the volume of the gas was recorded at time t and conditions where the molar volume is 24, and it's given as acid 1 released 20 centimeter cube, acid 2 released 1.2 centimeter cube of the gas. Give the name of the gas produced. So when we react an acid with calcium carbonate, so an acid plus calcium carbonate, this is going to release the carbon dioxide gas. Now we have to calculate the maximum volume of the gas at the end of the reaction, and we need to give the answer to 3 significant figures. So the acid is the limiting reactant, and it's the limiting reactant because they mentioned over here that we're using 10 grams of CaCO3 in excess. So the acid H plus will be the limiting reactant. So over here, we're going first to write, I wrote the net ionic equation. And the net ionic equation is 2H plus CO3 2 minus is going to give H2O plus CO2. The H plus will be the limiting. We need to find the number of moles of the acid. We do C times V. And the concentration was 0.1. The volume was also 0.1 liter. So we get an answer of 0.01 mole. Then using the coefficient, we can get the number of moles for the CO2 that will be produced, which will be the number of moles of H plus divided by 2. And this is the number of moles of CO2 that will be produced. Then in step 4, I will use the formula N equal V over Vm, where V is equal to N times the molar volume. And I got the number of moles. I multiplied by 24. This is the volume. I change it to milliliter. It will be 120 milliliter. So you just have to know that when we react an acid, a monoprotic acid with carbonate ion, this is what we're going to have. This is the net ionic equation. As we know that, let's say, for example, if we consider HCl and we react it with CaCO3, then we're going to get CaCl2 plus CO2 plus the water, which is H2O, and the gas will be CO2. And of course, we need to balance. This is going to be 2, and now it's balanced. So the volume of CO2 is 120 centimeter cube. Now the next question was, classify acid 1 and 2 as strong or weak acid. I need to know that a strong acid releases more H plus ion than the weak acid of equal concentration and volume. Therefore, if you look over here, we can find out that acid 1 released more CO2 gas. This indicates that acid 1 is a strong acid, whereas acid 2 is a weak acid, because the CO2 release depends on the H plus ions available. So a strong acid of the same concentration and volume will give more H plus ions, leading to more carbon dioxide being released. Now, if acid 1 is added to a solution of NaOH, and we already found out that the acid 1 is a strong acid, it gives the H+, and it reacts with a strong base like OH-, write the net ionic equation. This is a strong acid, strong base reaction. The net ionic equation will be this one, which is H+ plus OH- giving H2O. For question 5, consider the acid HNO3 and HNO2. Write their dissociation reaction with water. Now we need to know that when we have extra oxygens, this can pull electron density away from the acidic hydrogen. In other words, when we have more oxygen, the H plus will be released more easily, as in the case for HNO3. And we need to be familiar that HNO3 is a strong acid and HNO2 is a weak acid. So a strong acid with water, we will use a single arrow. We need to know that HNO3 is the acid. It will donate H plus to water, forming the hydronium ion H3O plus and the NO3 minus ion. For HNO2, it's going to be a weak acid. We're going to use a reversible arrow. We're also going to have an H plus being donated to H2O to form the NO2 minus and the H3O plus. Now the next question was, identify the strongest acid and the strongest base from the conjugate acid base pair present in the previous equation. So HNO3, NO3 minus, HNO2, NO2 minus. We also have the H2O and the H3O plus. And we need to identify among the list the strongest acid and the strongest base. HNO3 is a strong acid. It's even stronger than H3O plus in terms of donating H plus. However, we need to remember that in water, HNO3 donates its H plus to water, forming the H3O plus. In other words, the H3O plus is the strongest acid that you're going to observe in the aqueous solution, and this is referred to as the leveling effect. So no matter how strong an acid is, it's going to become H3O plus in water. So it's like the ceiling in aqueous solution. There is no stronger acid than, if you want to talk about H3O plus, that you can observe in water. Therefore, the strongest acid is going to be H3O plus. Now for H2O, NO3 minus, and NO2 minus. Now H2O is a weak acid and it is a weak base. The NO3 minus and NO2 minus are the conjugate base of the acids. This is the conjugate base of HNO3 and this is the conjugate base of HNO2. So let's go over NO3 minus and NO2 minus. There's a rule that we need to know, that the weaker the conjugate acid, the stronger the base is going to be. And that the stronger the conjugate acid, the weaker the base. So NO3 minus, the conjugate acid of NO3 minus, if you add an H plus, it's going to be HNO3. This acid is a strong acid, and if it is a strong acid, then it's going to lead to a weaker base, which therefore NO3 minus is a weak base. Now NO2 minus, if we add an H plus, we can find its conjugate acid, which is HNO2. It is a weak conjugate acid for the NO2 minus. Therefore, the NO2 minus is going to be a stronger base than NO3 minus. So these are the rules that we need to remember when we want to differentiate between or want to compare which acid or which base is stronger. So NO3 minus is a weaker base than NO2 minus because the conjugate acid of NO2 minus is weak. Therefore, the NO2 minus is going to be stronger than NO3 minus. It's even going to be stronger than H2O, as H2O, which is a weak base, the conjugate acid of H2O is H3O plus. This conjugate acid of H2O is a strong acid, and it's going to give H2O or determine that H2O is actually a weak base. So therefore, the strongest acid is H3O plus, and the strongest base is going to be NO2 minus, as it comes from a weak acid, whereas NO3 minus comes from a strong acid, that is HNO3, and H2O comes from a strong acid. And as we said, the weaker the conjugate acid, the stronger the base is going to be. Now they said compare the pH of these two solutions. So we have the same volume, the same concentration for a strong acid and a weak acid. Now, of course, a strong acid will dissociate completely to give H+, whereas the HNO2 will dissociate partially. A strong acid will increase the H+, in the solution, leading to more concentration of H+. As concentration of H+ increases, the pH will decrease. Therefore, the pH of this solution is going to be less than the pH of solution 2. For question 6, they said a strong acid react with a strong base. This is we went over it before, and when we have a strong acid, strong base, this is going to be the net ionic equation. And this net ionic equation, or the equation in which we have an acid with a base, it could be a strong acid, strong base, or it could be a strong acid, weak base. If it's an acid and a base, then we call it a neutralization reaction. Now, HF and NH3 both dissociate in water, write their dissociation reactions in water. So HF, and we need to be familiar that it's a weak acid, and NH3 is a weak base. Therefore, they will dissociate partially. HF will give H2O H+, and the H2O will become H3O+, and we will have F-. NH3 is a weak base, so it's going to accept H+ from the H2O, and will form NH4 plus OH-. Now for question 6, they said identify the strongest acid, strongest base, weakest acid, weakest base. So this is a similar question to the one we did before. Now we need to know that H3O plus is going to be the strongest acid, as any acid stronger than H3O plus, whether it was HNO3, is going to give H3O plus ion. It's not going to remain free in water. It's going to become instantly H3O plus. And we need to know that the strongest base is OH minus, as any stronger base than OH minus will react instantly with the water and form the OH minus. And we refer to this as the leveling effect. Therefore, the strongest acid and the strongest base is going to be H3O plus and OH minus respectively. Now we want to go over the weak acids. So HF is a weak acid. NH4 plus is the weak acid because it is the conjugate acid of NH3, and NH3 is a weak base. So HF is a weak acid and NH4 plus is a weak acid. However, H2O is a very weak acid. It has the Kw, which is equal to 1 times 10 to the power minus 14. So it's going to be weaker than all of the acids over here. Now, if you go over the bases, we said that the strongest base is going to be OH minus. As we mentioned before, that the OH minus, any stronger base than OH minus will react instantly and will form the OH minus, and refer to this as the leveling effect. Now, if we want to go and find out the weakest base, we have the option H2O, F minus, and NH3. Now, these two, they come from the conjugate acid. F minus comes from HF, which is a weak acid. NH3 comes from NH4 plus, which is also a weak acid. However, H2O, the conjugate acid of H2O is H3O plus, which is a strong acid. And the stronger the conjugate acid, the weaker the base is going to be. So this is the weakest base. Therefore, the H2O is going to be the weakest acid and the weakest base, and H3O plus is going to be the strongest acid, whereas OH minus is going to be the strongest base. Question 7. Classify each of the above acids as strong or weak and explain why. So we have perchloric acid and we have hypochlorous acid. So I just want to mention a rule that when we have more oxygens around the central atom, this is going to lead to a stronger acid. And this applies when we're comparing similar acids like HNO2, HNO3, and when the central atom is negative, highly electronegative, as in this case, HClO4 and HClO, or HNO3 and HNO2. So if we look at the structure of HClO4, this one has more oxygen atoms, and when we have more oxygen, these oxygens are, because oxygen is electronegative, it's going to pull electrons away from this bond, the OH bond. And as it pulls electrons away, the H plus will be released more easily than in this case where we have less oxygen. Therefore, HClO4 is classified as a strong acid, whereas the HClO, where we have less oxygen atom, is classified as weak acid.